Welcome, welcome. We're now on page 3 of the apportionment notes, and in this video we're going to discuss Jefferson's method. And Jefferson is, of course, Thomas Jefferson, and it's this apportionment that was adopted by the first Congress to apportion themselves, I guess, to the colonies, which were now the states. So this was a contemporary method of Alexander Hamilton's, which we discussed in a previous video. So we're going to learn Jefferson's method in the context of apportioning buses to bus routes. So imagine you're a town and you have these 6 bus routes, you have 125 buses. How can you fairly distribute those buses? And the relative size of the bus routes is going to be indicated by the ridership. So for instance, Route C should have about twice as many buses as Route E because it has about twice the ridership. So the things that we're going to need in order to calculate the apportionment is this idea of having a divisor. So a divisor that kind of represents how many riders per bus there should be. So let's start with building what's called the standard divisor by looking at the number of riders per bus if everything were apportioned perfectly. So if apportionment were perfect, then each bus would carry the total number of riders that's riders divided by total number of buses. Buses. So we need that total number of riders, and that's going to just be equal to all of the riderships added up. So 45300 plus 3107 plus 20490 plus 14160 plus 10260 plus 8720, and it's a even 130,000. And then divided by the total number of buses, 125. We can just do this to get 1040. This is riders per bus. And we can use this so-called standard divisor. So this thing is the standard divisor. Use this standard divisor to determine the ideal fair apportionment or quota. And we'll call this the standard quota. That's what we called it in the previous videos. So, for example, A should get 45,300 divided by 1,040 equals 45,300 divided by 1040, 43.558 buses, right? So this is total ridership divided by riders per bus gives total number of buses. And we can do that same division for each ridership value and get the proportional or standard quota. So let's kind of organize this into a table a little bit more. So let's use a different color here. So we'll have route, and we're talking just our routes. A, B, C, D, E, and F. Their ridership. And this is the 45,300. And then we'll have the standard quota, which comes from the standard divisor of, for A, 43.5 8 buses. And now let's just do that for the rest of the routes. So 31070 is the ridership for B. So 31070 is 29.875. C will have 20490 divided by 10040. And of course, we're going to have to make some adjustment here because we can't pass out a fractional part of a bus. And, but this is just the place to start to see kind of what is proportionally fair. And it will also give us an example to work with on how Jefferson's method is done. So after we get these numbers recorded, we can move forward. And finally, 8720 divided by 1040. 8.385. So if it were possible to distribute a fractional part of a bus, then these are the numbers that you would choose. Now, Jefferson's method uses the lower quotas, which is to say the integer part, which is to say rounding down the standard quotas. So let's fill out yet another column in this table. It'll be a lot like Hamilton's method, in that we start with the lower quota. So the lower quota be 43. This is not conventional rounding. This is just the integer part of the numbers. So there's no wondering about should they round up or down. It's just always down. And then we ask ourselves, how many buses? So now we're in Jefferson's method mode. How many buses did we distribute? So let's add that up first, actually. So we did 43 plus 29 plus 19 plus 13 plus 9 plus 8. 121 buses. So using the standard quotas, the standard divisor and lower quotas, we used or distributed 121 buses. So we used the standard divisor to build this standard quota, and then the lower quota from each of those is what our apportionment could be. But that only uses 121 buses. And by only using 121 buses, you still have 4 buses left over. And Hamilton's method, this is your starting point, and then you pass out 1 bus at a time. The first bus would go to route B. But in Jefferson's method, you want to stop at the lower quota. So in Jefferson's method, rather than adjusting what you have from this divisor, you just go back and change the divisor. And this divisor was chosen, it was a good starting point because it was the perfect proportional system. But there's nothing limiting us from changing that divisor. So Jefferson says, try a different divisor. You have to pick another divisor. And you have to decide on what the divisor should be. In this case, because we have buses left over, we should choose a smaller divisor. Because if we divide these ridership numbers by smaller numbers, then these quotas will go up. And when we round them with the lower quota rounding, then these numbers will also go up. the total sum will go up, and we'll have distributed more buses. So we have to make an educated guess as to how big our divisor should be if we're trying to increase or decrease this number right here. Because we're trying to increase the number of buses that we distribute, we decrease the divisor. Let's try 1,000 because it will make the divisions easier and it's also smaller. So here's kind of like, I don't know, some filler. You're just like, try a divisor of 1,000. Not 1,000 factorial, let's just do 1,000. So then you'll have a new column for quotas. So this will be kind of like a modified quota because we modified the divisor. Dividing by 1,000 is relatively easy. You just move the decimal place over. What are we dividing 1,000 by? It's these ridership numbers. So notice you can do these without a calculator. The lower quota is, again, just the integer part. And you can see that some of these numbers have gone up. We had 43 buses given to A with the standard divisor. Now we're giving them 45 buses. Where some of them has not changed. F got 8 buses in both cases. But let's add up and see how many buses we used. Let's see, that's going to be hard to see. 45 plus 31 plus 20 plus 14 and 10 and 8 makes 128 buses. So with a divisor of 1,000, we apportion 128 buses using the lower quota. So that's too many. So we have to go back and yet again change this divisor. So we changed it from 1,040 to 1,000, and now we need to make the divisor different. And we should make the divisor go up so that these numbers come down. So hopefully you can get to 125. And now you're in a bit of a guess and check game. And so there's a lot of calculations here, a lot of arithmetic, so there's a lot of typing into a calculator. And with that comes room for error. So it's my suggestion that you use a spreadsheet that automates this, where all you have to do is type in the divisor that you want to guess, and the remaining calculations are all handled by a computer automatically. And so I have done that for this exam, for this situation, and the next divisor that I chose was just halfway between 1,000 and 1,040. I chose 1,020. So we're going to divide all of these numbers by 1,020. We'll get a list of decimal numbers. We'll round all of them down, and we'll add them up. And whatever they add up to, that will be what we in total apportioned. If that number is equal to 125, then that's the completion of Jefferson's method. And that's how many buses you hand to each route. So let's look at this table in which that happens exactly. The seats available is buses here. The states are the routes, and the population are the riderships. Those words are the traditional words that are used in apportionment problems, because normally when you introduce apportionment and talk about apportionment, the most pressing example is that of apportioning seats in a representative branch of government to the different states, and the states are measured by their population. But being able to identify that the seats available are buses, the states are routes, and the ridership is the population allows you to interchange the pieces and let go of the requirement that these particular vocabulary words are strict. We don't there's a fluidity in this naming scheme, but the roles played by these numbers are static. So we have also the divisor. And so what this is saying is all of these numbers are being divided by the divisor, which gives the quota column. And then we've rounded the quota with the lower rounding scheme, where all we do is give the integer part. 44, 30, 20, 44, 30, 20. We don't even pay attention to the decimal part. 13.8824 gets rounded to 13. 10 and 8. When you add up these numbers, you get 125. That's how many buses we had in total. That means Jefferson's method is done with. You give 44 buses to route A, and so on. We can see our prediction from earlier that route C should get twice as many buses as route E because the population of C is twice that of route E is apparent here. And so that's Jefferson's method. And in the coming videos, we'll use a similar idea with a different rounding technique. We'll have freedom over the divisor and just change it until the apportionment is perfect. We still get a close to proportional system. It's just a slightly different mechanism for getting there. Okay, see you in the next video.